Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 17, 2025, about 3 days ago. The big hook is that this paper introduces a hybrid method, called RPC, that matches self-consistency accuracy while cutting sampling costs by 50% and making confidence estimates more reliable. The paper is titled, A Theoretical Study on Bridging Internal Probability and Self-Consistency for LLM Reasoning. And as we will see later, the implications for test time scaling are quite significant. In brief, it builds a theory for sampling-based reasoning, diagnoses why self-consistency and perplexity each fail, then combines them with perplexity consistency and reasoning pruning to get faster, more stable convergence across 7 benchmarks. Also, the authors shared the official RPC repo. You'll find Python code for RPC, self-consistency, and perplexity baselines, dataset and eval modules, a main script to run experiments, metrics and cache utilities, and setup via requirements. Ready to run commands and an all-XPS script, reproduce results for math, Methodicity, AAM, Olympiad Bench, and several math LLMs. Well, Figure 1 shows the RPC pipeline and why it speeds up confidence estimation. The left panel depicts large language model sampling, where multiple reasoning paths receive internal probabilities. The middle panel illustrates reasoning pruning, which means removing low probability paths so the estimator focuses on plausible reasoning. The right panel presents perplexity consistency, which aggregates those internal probabilities inside a self-consistency style vote so confidence converges faster with fewer samples. So Table 1 reports how many samples each method needs to beat self-consistency. It shows that perplexity consistency often matches accuracy while having samples on math. RPC meets or exceeds self-consistency with fewer draws on Math Odyssey and AIME, which signals faster convergence because low probability paths are pruned. The deltas suggest stable or improved accuracy. Reduction rates reach about 50% on several datasets, and the maximum drop is roughly 62%. So, Figure 2 shows accuracy rising with more samples, and the red RPC curve consistently leads, which signals faster and steadier convergence. Perplexity consistency means using internal token probabilities inside a self-consistency style vote, so the estimator benefits from both signals. On math, the left panel shows RPC pulling ahead as n grows, outpacing self-consistency and perplexity. On AIME, the right panel shows the same pattern, with the gap widening at larger budgets. So Table 2 reports accuracy and expected calibration error across 4 math datasets with the intern LM2 Math plus 7b model. Expected calibration error means how far predicted confidence diverges from actual correctness, so lower values indicate more reliable confidence. RPC posts the best or tied accuracy on most datasets, with about 52% on math. It also shows consistently lower calibration error, near 6% on math. On average, RPC leads in accuracy while achieving the lowest expected calibration error. Alright, 2 takeaways stand out. First, a clean theory separates estimation error from model error, explaining why self-consistency is slow, while perplexity can mislead. Second, RPC merges the best of both, matching accuracy with roughly half the samples and better calibration. The implication is cheaper, more reliable test time scaling. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.